Okay, so so we're starting. We just want to kick off from where we stopped last class. So today I'm going to start from. Okay, yeah. I think this is where we stop. So let me just start from histogram. What we're trying to do, visualization, starting from histogram. So I introduced us to matplotlib, which is one of the plotting library in Python. Or because as a data scientist, there are some tools that you need to familiarize yourself with. We've talked on pandas, which is used for data manipulation, data cleaning and all of that. The next thing is matplotlib, which is used to visualize your data. Because when you have data, you need to, before you go ahead, like I said, machine learning is the last thing you will ever you would do as a data scientist. So when you have a data, you need to explore the data. You need to visualize the data. You need to wrangle the data. Just check the data to draw insight out of the data. So visualization is one of those key things which will quickly help you see what is going on in the data, the relationship between between two or more features, things like that. So we started with matplotlib, and then now we want to look at Seaborn. Now Seaborn is built on top of matplotlib. Seaborn does not exist alone. So it's built on it, meaning that we can use both the Seaborn and the matplotlib together. So we can start with the Seaborn and then use the matplotlib to fine-tune our visualization. So the norm when you want to start is to import Seaborn as anything, but the norm is to use SNS, Seaborn. So there are some data that actually that are pre-installed in Seaborn. And one of the data is what I use as the tips data. How do you load the data? You use the load data set method on the SNS. So if I do that, this is just my data. That's the tips data that come pre-installed in Seaborn. So you can also run that on your computer. So suppose I want to plot a histogram. First, what is a histogram? A histogram is a plot that we use to display a single quantitative variable. By quantitative variable, we mean a numeric variable, numbers, variable that has numbers, things like that. So like here, we can see the total bill is a quantitative variable, tip is a quantitative variable, size is a quantitative variable. Like all these sex, smoker, day, and time, these are categorical variable. In Python, it saved them as objects or categorical variable. So suppose we need the histogram of total bill. So you can see now I import matplotlib. So here I want to use matplotlib, and I will just to finish the matplotlib that we started. Okay, so I import matplotlib.pyplot. Pyplot is a module in matplotlib that we use to visualize the data. So I import that as PLT. So in matplotlib, so the histogram is in the hist method, and I want to plot the total bill in my tips data frame. This bins is optional. I can remove that and plot this. So by default, look at what it gives me. So if I want to change the bins is just that's like the bars, like the number of groups you want to put your data. So I can decide to use 10 bins that, give me this histogram grouping my data into 10 places. So I can do that. So it's going to give me that. I think this is similar to the default, but you can use whatever number of bins. That's why in statistics, we do not actually recommend histogram, because the bins, if I use 5 bins and someone else uses 10 bins, you are not going to get the same histogram. But I mean, it's good, but it's not really, as you move forward, you will realize that it's not one of the best plots to display your data, because it's subjective to the number of bins, but it's good at least to play with. So here you can, we visualize the histogram our total bill using histogram, and then you set the number of bins. Now, I showed you two different methods to use matplotlib. One is by, just calling your plt.is and all of that. The second is to first create a figure. So here, the first line here, I created the figure, plt.figure, and I saved that as a variable called fig. And then I also create an axis, that's the second line, where I called my figure that I created and I had a subplot. Now, how do you know what should go inside this subplot? Put your cursor there and press Shift Tab. If it doesn't show you anything, sometimes you may need to run that cell and then come back and put your cursor there to press Shift Tab. So see some things. So if you press this plus, you see add subplot, see the argument, number of rows, number of columns, and index. So here I supply number of rows to be 1 and number of columns to be 1 because I just need a single plot. If I need 4 plots, 2 rows, 2 columns, I will put 2, 2. Index here tells you the position you want to put your plot. So since it's just a single plot, that's why the index, the third argument here is index, just 1, because I just need a single plot, meaning give me a plot with 1 row, 1 column, and I want it also in the first position. So that's the index. If you put 2 there in that third argument, I'm sure it's not going to work because you have 1 row, 1 column. Okay, so that's what this first line is doing. And the next one, I have created the axis on the figure in the second line. So everything I'm going to plot now is going to be on the axis. So that's why we call the east argument on the axis we've created in the second line, displaying the total bill in tips data frame. Then, so here, now if you're using axis, you're not going to be using X label like here directly or Y label or title. You're going to be using set method. You want to set the X label to be frequency, you set the Y label to be total bill, and you set the title to be histogram or the whatever you want as a title. Then you can run that, and it's going to give you this. The same way you can as well, it has bins argument. You can see bins. I didn't pass anything, but you can choose the number of bins you want, So that's that about the histogram. So now let's look at box plots. So because we use box plot to display, you can use that to display categories like the quantitative variable in different that you have. Like you can use this box plot to display the categorical variables, like even 2, unlike histogram that you just have. Although histogram is for quantitative variable, so we can use this to display one. So suppose we want to display the tip, we want to look at the relationship between the tips that female and male actually give to people after, maybe buying, food or in a restaurant or something like that. So first, I want to subset my data frame to have 2 separate data frames, one for male, one for female, in my tips data frame. So let's call that of female to be this. That's the variable I'm using. You can choose to use another one. So here now, I just want to subset. Okay, so where the sex here is female. So I can do that too for male, tips, male. Okay, so I have my data frame now for both male and female. Now I want to plot box plot. I want to use box plot to display the tip given by male and female here. So I can use the PLT dot, let's use tab, press tab to see what you have there. But I have bar, I have box plots there. So if you don't know what to do, just once you put your cursor inside, just press Shift Tab. So you can see I have X here. What is X standing for? X stands for the array or sequence of vectors, the input data. So what should go in there? I need to put in the tip, maybe for female or for male or for both. So suppose we just want to visualize the tip given by female. So get my female's data frame. Okay, and then I want to display the tip. Tip is actually a single variable there. So this tip column is what I want to display. So tip there, so I can decide, you know, let's say I want to give it label. You already know that X label. X label, that should be, you know, female. And I can give it Y label just the same way, Y. Okay, so my Y label should be tip. I can decide to set title, but suppose I'm lazy on doing that, just push show, you know, you can see. So you have a box plot for female, telling what do you have in box plot. What box plot here, this line at the middle gives you the median tip given by the female. This is a box and whisker plot. This last whisker here, this line here, is showing you the lower quarter. No. This is giving you the lower quarter here, this line here, and this is giving you the upper quarter. This is just telling you the range of your tip given by the female. This is an outlier. This is an outlier. So this is the lower quarter, the upper quarter, the median. This is giving you the minimum and the maximum. The minimum is this, the minimum tip given by female, the maximum tip given by female, and this is just an outlier. Okay, so suppose I want to put both male and female together. All I need to do in that box plot is to pass a list, just a list for both male and female. So let me put that of male there and display the tip also. Okay, but I want to put label for both of them. So we have an argument called labels here. Okay, so I can put labels, put that on the next line. Just enjoy it, you know. Okay, female, male. Let me change the label here, X label. Let's put sex. Okay, you can see. So this gives me the box plot for both male and female. So here you can, you know, compare the tip given by male and female. It looks as if we have some men who are actually, I don't know, this is not an insult. I think most females are very stingy, you know. So here we can see that there are some extreme good, you know, male that gives even SS tips. Those are the outliers there. So you can compare their median, the lower quartile, the upper quartile, the minimum tip given by male, the minimum tip, maximum tip given by male, and you know, you can just compare them like that. So this is how to display your box. You can set title, just plt.title, you know, like that. And so this is just an alternative method of doing that using the set argument, which like I showed you, so you can go through that. Okay, so let's move mainly to Seaborn. So like I said at the beginning, that Seaborn is built, you know, on top of matplotlib. It's actually more advanced a little bit than matplotlib, and is mainly used for statistics, you know, to produce statistics graph, things like that. So suppose we want to use this same tips data set, and so let me run that. Then we want to display histogram. By default, to display histogram, we use the sns.displot, but by default, if you use that method, it gives you both the histogram and the density plots together. So like here now, I create my figure and my axis. This is a method we used last class. If you want to put the figure and the axis together without, but here now I'm using figure and axis. I create a subplot. You can check what is in there. You can check it. So you can see by default, the number of rows is 1, the number of columns is 1, but I can overwrite that depending on how many plots I want to display at a time. Okay, so I didn't put any argument because it already have default row of 1, 1, and that's what I want to use. So on this my axis that I created, that's what it is on top of it. I'm plotting the histogram, sns.displot. Then I plot the total bill in my data because that's what I use to load the tips data. Total bill there. I set the title, then it will show it. So by default, it's going to overlay your histogram with the density plot. This is the density plot. It's called kernel density estimation. How do you, so you can check, you can check it, you will see the parameter that actually gave us that, see, KDE equals to true. If I set this KDE to false, it's just going to give me only the histogram. So, and that's what I did here. The same thing, I only set the KDE parameter. KDE stands for kernel density estimation. So I set that to false. So then it gives me just the histogram there. I can also display just the density plot. What argument will you use? If you press Shift Tab, you see that. You see histogram is true. If I set the histogram to false and leave this KDE to be true by default, it's going to give me just the density plot. So, and that's what I did here. The same code, the only thing I'm changing here is this second parameter here. So I only set the histogram to be false, and I leave the KDE parameter, and I leave the KDE parameter to be, to be true. Then you can display that. So if I do that, the density plot. So the final thing I'm going to do here before we move to machine learning is the bar plot or the count plot. And I'll quickly show you the difference between both. So normally bar plot or bar graph, we use it to display a count or to display discrete values. By discrete, it means categorical variable. We mean object variable, So this first line should be common now. Create the figure and the axis by uplt.subplot. Like I told you, the default number of rows is 1, number of columns is 1. It doesn't have the third argument for index, no. So you don't need that. So this first line is actually plotting on this axis the count plot. If you want to know more, you can just put your cursor there, Shift and read more about it, and then you know. So you can see my argument. These are arguments you can pass in. This X, whatever, that's what you want to display. Y, but which is optional. U is the argument to, like for color. You want to use this. U is you have a color argument, but U is also, you can pass in like what I want to use to divide my data. That's the EU argument. Like I can pass in another variable that I want to use to separate the bar graph. That's what you will see it as we do scatter plot on the red. So that's this second line is actually the one that actually plot our data. So I want to plot the day variable, this day. I want to plot that, and then I will pass in my data. So I can set. So here I set the X label, set the Y label, and then show it. So if you do that, it gives you the plot. So I can see the day here. You can see that it looks as if you have more counts. Saturday is actually more dominant in our data. So, things like that. So if you want to use bar plots, in bar plot, the difference between this bar plot and count plot is that you have to supply the count for each of these categories here. And that's why we are passing the Y argument. I want to supply, unless I want to just look at the day, I want to supply the tip for each day. I want to visualize the tip for each day in my data. I can use the bar plot. Okay, so X label, Y label, and show. If you do that, you have this. So some might ask that, what are these lines for? These lines are just the means, the average for each day. Average tip for each day. Is this what that's what this line represents? So you can see that it looks as if the tip on Sunday is actually much more higher than all other days. So that's what you can use bar plot to do. And finally, scatter plot. A scalar plot is a plot that is used to visualize two quantitative variables. So why am I defining all of this? You need to know what each plot can be used to display. That's the truth. If I pass in categorical variable into a scalar plot, it's going to give me error. So you need to know that scalar plot can only be used to visualize two variables. Now I want to separate, so this first line is the same. Second, SNS does scalar plot. Your X, this X is what I want to put on the horizontal, the X axis. Y goes to, I want to display the tip, that's the Y axis. The hue argument is what I want to use. I want to separate, I want to look at the distribution of this tip for both male and female. That's why I'm passing this hue argument. I want to separate those tips in this for this total bill, by sex, by male and female. They're my data. So my X label, my Y label, my title. If I show that, and it gives me that. So I can see there that male. You can see it looks as if male gives actually more tip as their total bill. So the more the higher the total bill of male, the more the tip they give actually. Female is not so true, but I mean they also have that trend. So I don't want to believe that females are more, they don't give tips to people like that. But I mean it could be true based on this, but we are not establishing any hypothesis here. Okay, so that is what that's the end of this, and then we can start machine learning. So any question before we look at machine learning? Any question on that? Any question? Okay. Okay, so can you see the screen for machine learning before I move on? I need someone to confirm, please.
Yeah.
Yes, sir.
Yes.
Oh,
Yes, sir.
okay. So the question is, what is machine learning? I know this is a big word. You've been hearing that. You've heard some people say that. It used to sound like a kind of a big word out there. Machine learning, machine learning, machine learning. I'm going to try as much as possible to demystify machine learning today, to break it down. I'm really going to trust God to help me to break this down. Now, by definition, and I'm going to explain what this definition means. The machine learning is the process of programming computers to optimize a performance criterion using example data or past experience. So let's talk on that. What do programming computers in the past, programmers, computer scientists, what they do is when they program, like they write programs, rules for that you can establish to map your input data to get an output data. All they wrote rules. Those who did computer science here would testify to this idea of gates, log or gate, XOR gate, AND gate. Those were rules that were used to map inputs to output. But those rules are susceptible to mistakes. They are not so much. I mean, they have limitations, weaknesses, things like that. So that's the idea of that's where machine learning comes in. That can we, instead of trying to program rules for computers, can we give the data? Can we give the computers data, past experience, history, historical data? Let that computer look for patterns in those data, establish relationship between the variables, between the features and the output, and then come out with his own rules, which we call function. His own rules, which we call function, to map input to output. That's actually what machine learning is all about. But the main goal in doing that, we now want to monitor the rate at which the computer is making mistakes. And that's what we call error. That, okay, is making mistake while trying to establish a function that will map your input data to output data. So mainly your goal as a machine learning engineer or a data scientist will be to maybe like build a particular model, build a machine learning model that will map input data to output or to label. I will talk on all of those terms, you know, with the minimum error, minimum possible error. Now, I use the example data, meaning historical data. For instance, let's look at a patient. Suppose in a hospital, you're working as a data scientist in a health organization, and you want to build a predictive model. When I mean predictive model, model to predict, you know, a predictive model that we determine whether a patient or has, you know, cancer or not. That's your goal. What will you need to do? You will have to look at all the history, like the historical record of patients. So, you know, you will need to supply that. You need to have access to historical data of patients. Look, their age, you know, their whatever the record contains, you know, maybe their age, the eye, the blood pressure, and BMI, all of those things. Because, so it is from those historical data, that's what we call example data or past experience. So the machine learning algorithm is going to be looking at those features, those variables, and the output, whether that patient or some other patient that has that variables has cancer. So if that machine learning algorithm is able to discover those patterns, if you supply it a new data of patient that has something similar to those features it has already seen in the data you use to train, it's going to tell you whether the patient will have cancer or not. That's what machine learning is doing. Okay, so don't worry, you will get a good hand of it as we go on. Now, we have mainly three types of machine learning. I mean, it depends on the book you are reading, but mainly there are three types. We have the supervised learning, the unsupervised, and the reinforcement learning. Some textbooks will tell you supervised, unsupervised, semi-supervised, you know, and reinforcement learning. I mean, depending on is how each person, you know, view it. I mean, they are not wrong. No one is wrong, no one is right. So it depends on the school of thought that you're coming from. Now, by supervised learning, the example I just gave you now is an example of a supervised learning. What makes it supervised? What makes it supervised is that you already know the output you are expecting in advance. What's the output? Patient has disease or not. So that is also part of the data. Once you have in your historical data or in the data you have available, your training data, if you have a column for the output, that whether this patient has a cancer or not, if that column is part of your data, if that label, that is part of it, then that is a supervised learning, meaning you already know the output you are expecting. So you use that output to train your algorithm, to train your machine learning algorithm such that, but your goal of using it to train it is so that by the time you now give that model that you have already trained with a known label, if you give that model a new data that does not have the label, it's going to predict it correctly. So it's like you are using teacher. You have a teacher that you are using it to train a particular input data. So that is what supervised learning is. As I said, it's used whenever we are interested in predicting output from the given input data. But it consists of input and output pairs. The output is what I mean by label. What your goal, what you actually want to predict. So, and that's what constitutes your training set. But what is the goal of this supervised learning? Your goal is not actually to predict on the training data, the data you use to build the model. No, you're only using that data to build the model. But your goal is that your model that you want to build it such that it can help you to predict new and unseen data. That's the truth, because by default, if you use a particular data to build a model, if you use that model again to predict on that same data you use, by default, it's going to give you good accuracy. Why? the model is not foolish. He understands that I was built using this data, so it will recognize all the patterns there. So that's why when you build a model, you must evaluate it using new data that the model has not seen before. And that can tell you how the model will behave when you give it another data that it hasn't seen before. And don't worry, we'll look at that too. So, but under the supervised, there are two common types of supervised learning. We have the classification and the regression. The example of predicting whether a patient has cancer or not is an example of classification, like whether you have this or this. Like in the projects that I gave as part of this training, it's also a classification problem that you want to predict whether a customer will be, I think, given term deposit or not, you know, or you want to predict whether a customer who applied for credit card will be approved or not, you know, things like that. So those are examples of classification. However, it's not always binary classification. It can be multiple, like multi-class classification. Like you want to predict whether, let's say you want to predict whether a particular image is a jean, a shirt, you know, and other categories like that. But the common one is the binary classification. Then the next one is regression, which is also part of supervised. And the goal is to predict a continuous value. Like you want to predict the housing price, you know, the price of a particular house, given its features like the location, the number of occupants, the income of those occupants, the geographical location, things like that. Or you want to predict the price of a goods, you know, things like that. Those are regression problems. Anytime your goal is to predict a continuous value, then you are dealing with regression. If you are to predict categories, whether this or this, then you are dealing with classification. Why am I taking time to explain all of this? Before you build a model, even after exploring, after visualizing, you must be able to ask yourself, what kind of problem am I dealing with? Am I dealing with supervised learning? If the answer is yes, what kind of supervised? Am I dealing with classification? Am I dealing with regression? Because each of these has different algorithms. You cannot use a regression algorithm to train classification problem. It's not even going to give you, it's going to give you error, and if you manage to run, it's going to give you wrong output. So that's why you need to know that. Now, the other types, unsupervised, is beyond the scope of these free training, and the reinforcement. Reinforcement is where you see the robotics and all of that. That's where you see reinforcement, you know, learning. So, but unsupervised is just the opposite of supervised, meaning all you have is just input data. You do not have the output. You don't have the label. Like you want to predict which goods. Let's say you are a data scientist working for a big supermarket, you know, a big, you know, supermarket, and your goal is to predict which product a particular customer is going to buy next month. Now, you don't know, because there are several groups. All you need to do, or you want to predict the goods that will actually move very fast next month. All you can do, that can fall under customer segmentation. Like you want to group their customer based on their favorite, based on the goods that have been doing. So that's an example of unsupervised. And under that, you talk about clustering and all of that. These are things we will go into more detail in our machine learning master. So it's beyond the scope of this free training. But for this, I just want to focus on supervised and then classification. Okay. So now you will also hear these terms in the wild: generalization, overfitting, underfitting. Let me quickly talk about that. So, you know, I said that in supervised learning that our goal is to build a model from a training data that can make accurate prediction on test data. Test data means new and unseen data. Now, what we mean by generalization? Generalization means that you want to achieve good accuracy on your training data and as well on your testing data, much more on the testing data. You really want your model to be able to predict accurately unseen data. Because if your model do well on the training and it doesn't perform well on the testing, you have not built a model actually. That's the truth, that you have not. So there is more emphasis on the testing data, on new and unseen data. Now, if your model perform well on training and as well perform well on the testing, then we say your model is able to generalize well. That's done by generalization, meaning it performs well on both the training and the testing. It generalizes well. Now, when we say overfitting means your model performs well on the training, but it performs poorly on the testing, on new data. That means your model is overfitting. Let me break that overfitting down. It means that your model memorizes the patterns in the training data, but when we give it on unseen data, new data, it's not able to see. It memorizes the patterns in the training such that when it now sees new data, it's confused. Like, what are the patterns there? Because he only memorizes patterns in the training. He didn't really learn. No learning there. He just memorizes. So we say that model is overfitting, meaning the accuracy on the testing data, on the new data, is low compared to the accuracy on the training. That's what I mean by overfitting. Underfitting is just worse. It does not perform well on the training as well as on the testing, meaning the accuracy on both is low. That's underfitting. So I've been able to explain what generalization means, meaning that your model is able to perform well on the new data, meaning it's able to generalize well. Overfitting, it performs well on the training, the data you use to build the model, but performs poorly on unseen data. Underfitting, poor performance on both the training and the testing. So the question is, how do we ensure that our machine learning model does not overfit? Because if you have good accuracy on the training and poor on the testing, you are not done as a data scientist. You are not. You need to go back again. So how do we ensure our machine learning model does not overfit? I will only talk on one when we get to building model. I will talk on one. Just keep this time on your mind. Regularization. Keep it. If I forget, remind me to talk about it. Okay? That's one way you ensure that your model does not overfit. Okay? The last thing under this part is loss function. Now, your model is that what you are doing. You see, what you're actually doing while building a machine learning model is to be monitoring your predicted output and the true output. You know, that's supervised. You already know the output. You have a label already. So when you are now checking the difference between what your model is predicting and what is supposed to be predicting, the true output, that's what we call loss function or error. They are the same thing. Cost function, loss function, objective function, they are all saying the same thing. And that's where optimization comes in. When you say you're optimizing, you mean when you hear people doing it, they say, oh, we're optimizing. It's not a big term. What it means is that we are finding function that will reduce the error our model is making when trying to predict output of a particular input data. So, and that's why I put it that it is one way. A loss function is just a function that we use to examine the performance of our model. How is our model doing? So the difference between what your model is predicting and what is supposed to be predicting is what we call loss function. Now, the loss function for regression is different from that of classification. And that boils down to what I said, that you must know the kind of problem you are working on as a data scientist. So the common loss function for regression is the MSE, the mean squared error. Okay? But for classification, we have cross-entropy loss accuracy, but I will only be using accuracy. If when we want to do the deep learning masters, then you will know more about cross-entropy. But I will focus on accuracy, at least. Accuracy for regression is where we are using the R square. Don't worry. I'm not sure we're going to do regression, but at least for today, we'll do a classification which is on accuracy. Okay, so the key principle, like I said here, is to ensure that the error our model makes in accurately predicting the output from the input feature is very low. That's the goal, because the smaller the error, the more the accuracy you are going to get, and vice versa. Okay, so these are some of the algorithms, the supervised machine learning algorithms you will hear: linear regression, logistics, support vector machine, k-nearest neighbors, and blah blah blah. For this training, for today we're going to look at logistic and k-nearest neighbor. Maybe next class I may look at random forest, because that's a state-of-the-art algorithms, things like that. So let's jump into k-nearest neighbor. I always start with k-nearest neighbor. And if you meet other data scientists, they will tell you the truth that one of the algorithms, if you're doing supervised machine learning, one of the algorithms to quickly start with is the k-nearest neighbor. One is very fast, it's easy to understand, things like that. Because when you are building a k-nearest neighbor, is simply storing your training data set. So when you want to make a prediction, like you want to make prediction for new data, what that k-nearest neighbor algorithm is doing is to look for it's going to take your new data point and check which of the training data point is the closest to this new data point. If it's able to find it, it's only going to assign the output for that training data that you used to build it to the testing data. You will see that as we go on. So that's what we call the nearest neighbor, meaning the closest point in the training to the testing that you want to test. So if it's able to see it, it's just going to assign it. Okay, that's if you are using just one neighbor. But you can also use more than one neighbor, like 5 neighbors. It's going to look at 5 data points in the training set closest to the new point, and look at the label of those 5 points. Now, it's possible that maybe 3 of the 5 points belong as one particular label, and the remaining 2 as one label. So there is voting. Voting is going to take place later. Okay, majority carry the vote. 3 of those neighbors belong to one class, 2 belong to the other class. It's just going to assign the label that has like 3 people that belongs to the new point, to the new data point, things like that. So that's what this nearest neighbor means. That means we are going to set the number of k. K is just number of nearest neighbor. By default now in scikit-learn that we're going to use, I think k is default by 5, but you will tune that. I will explain what all of that means. Okay, so let's move straight. So we want to look, there are some. Now we're going to use scikit-learn. Scikit-learn is a popular library for machine learning. Okay, as a data scientist, these are some of the libraries. If you go for an interview, you are ready now that you want to use this whatever knowledge you have now to get a job. They're going to ask you some questions. What library are you using for your machine learning? At least you should be able to talk of scikit-learn. Is the popular machine learning library used in the industry, not just in academics, in the industry to build machine learning. I'm not talking of deep learning now. I'm talking of machine learning. Okay, so scikit-learn. So there are some data sets that also come pre-installed in the data in the scikit-learn. Those are what we're going to use all through today and this training. So we have the iris data that comes there. If you want to know, this is how you do that. First, I think scikit-learn comes pre-installed with your Anaconda. I think so. If not, if you do import like from scikit-learn blah blah blah, if you tell you module not found, you have to run this. Let me tell you what to run. You have to just install it and use pip install scikit-learn. So if you get error, they just run this line pip install scikit-learn, and then you can go. Then it will install it for you. But you have to have internet on. Okay, so from scikit-learn, if I put dot and press tab, see, scikit-learn cluster, that's for cluster I mentioned. So this is the one I need for data set import. if you want to see all the data set that are there, we have the California housing. That one is used for regression, you know, to predict the price. So I need the iris. So it's in the load iris. You, in the activity you're going to do, you're going to work with load breast cancer. So suppose I just need this iris. Okay, so that's the data frame. The next thing is you have to instantiate that this data. Create an instance of it. Okay, let's call it iris. Okay, so we have load iris. So this actually create an instance of that iris. So let's see what we have in the iris. So this iris, check the keys, those things I have there. Run that. You see, I have in the way those data come installed in scikit-learn. They already put the data into one place. The target is our output, what we want to predict. They put it in another, you know, NumPy array. We have the target names, the name of your target. You know, this, if you want to know more about the data, run the description on it. Feature name, those are the variable names in our data. We can explore it and see. So suppose I want to see what is in the data. I can use this. Remember, I told you how that there are two ways to select a particular variable in your data frame. In your data, you can use the dot method, or I can use this data, whichever one you use. So you can see these are the data. They are stored as an array, a NumPy array. That's the way they come in scikit-learn. Okay, so you can see those are my data. But you can play with others. So suppose you want to see the target. See, so that means 0, 1, 2. Look at, they are already arranged. You can also check the target names. Okay, see, we have Setosa, that's the 0. Versicolor, that's the one that stands for 1, and Virginica, that's the one that stands for 2. So you can explore it. You can even check the feature names to see. Feature refers to the variables you have there. Okay, feature names. See, so that means we have 4, you know, different features there. We have the sepal length, the sepal width, the petal length, and the petal width. So you can play around to explore the data to see what you have there. Suppose I'm interested in converting it to a data frame. I showed you this last class, but I'm going to remind you. First, import pandas as PD. Let's call it iris df. Okay, so PD dot. I have to use this data frame. So data frame. This. So what do I want to add? I need to pass in my data. That's the iris data. Then I can set my columns to be the iris feature names. Okay, feature names. That's the, you know, that stands for my my columns, my variables. So I can just check the head, iris df dot head. I can check that. So you can see I already converted those NumPy array that I showed you to a data frame. So this is the first 5 rows of my data. The sepal length, sepal width, petal length, and like that. So if you are interested in looking at that, you can, just convert it to a data frame. I can check the dimension. By dimension, I mean the number of rows and the number of columns. So I can use the iris df dot shape, if you remember. So that gives me that I have 150 rows with 4 columns, 1, 2, 3, 4. Okay, the output is not here because it's stored in a different variable called targeting. So this is just the features, the main data, like that. So we can visualize it using, why am I doing all of this? When you have your data as a data scientist, your final goal is to build a machine learning model. Is to build your machine learning model, but you don't go there straight. That's the final thing you will do. You need to explore the data to draw insight. That's why you have to visualize your data. You have to check, do some data manipulation and all of that. Okay, so building the model is the final thing you will do. Okay, so suppose we just want to explore the data. Here, I'm interested in looking at the sepal length, the relationship between the sepal length and sepal width. You can try other variables there. Okay, so since they are continuous variable, they are numeric variable, I know I'm definitely going to use scatter plot. So I'm not using the seaborn, I'm using matplotlib. That's why I use plt.scatter. Okay, this is sepal length in my data frame, sepal width in my data frame, and I want to use the target, this output to separate that data, to look at them, okay, to see how the distribution of those variables, with respect to my target. So X label, Y label, all of this, you are aware of, all this one, okay? So you can see there is this what you see here, this purple or whatever color it is separate, separated between these other two. But there's not so much separation. What does this separation actually tells you? If your data is clearly separated, it will help the machine learning model to quickly discover the patterns in your data. But if they are not actually well separated, you can predict how your model is going to behave on that data. Meaning your accuracy may not be that high. That's why it's good to visualize, to have a kind of expectation of how your algorithm, how your model will behave, even before you build it. Because looking at this now, I know that my model may not actually, if these are just the only two variables I have in my data, my model the accuracy may not be that high. Because look at the sepal, this is Virginica and I think Virginica and vesicolor. They are not that separated. Only this setosa, this is kind of clearly separated from the other two. I mean, you can try others variable and just to check, to examine that. Okay, I think this is the same. Okay, this one is sepal length and petal length. And this is still far better, but here I'm using seaborn now. You can use matplotlib, it doesn't matter. I was just playing with the data. Okay, so I want to plot the sepal length and the petal length. You can see this one of the target names here, the setosa or whatever. This, you can see the black one. At least it's still a bit separated compared to the sepal length and sepal width. Yeah, I'm using sepal length and petal length. So it's still a bit, clearly separated. So I can know if these are the only two variables. Ahead of time, I can predict how my model will be able to discover the patterns here to build, because the goal in using iris is to predict the species that a particular flower called iris belongs to. We have three species. We have the setosa, the virginica, and the vesicolor in this data frame. And these are the three species. So that's the goal. That's what we want to build a model to predict. So here we can see that, okay, I think the model is able to, that there is a kind of separation, clear distinction between these three colors here, between these three species here. So, I mean, but suppose we want to visualize it together. This method, I must warn you, this pair plot is only good if your data is not so big, okay? So if your data is small, like the one we have here, 150 rows, four columns, I mean, it's good. Because pair plot is going to pick display two features at a time. Like give a visualization for two features, taking them at a time. So, okay. So since we have four features, so it's going to do that for us. So is in the pandas plotting library. So pd.plotting.scatter matrix. You don't need to memorize, like I told you. If you put pd and put dot and press tab, you will see the plotting, and then put dot again and press tab, you will see the scatter matrix. This is my data frame. I want to separate it with this color. C stands for color. That's, I want to separate it with the target. Remember the target, I have 0, 1, 2. This is the fixed size. These are optional arguments. This fixed size, meaning the size of my figure. This marker, meaning I want it to give me circles. This size, 660. You can play around them, and you can choose not to use it. It's going to give you, but I want it bold. That's why I said the size argument. So if you do that, it's going to take some time and then see. So here now I can look at the relationship between any of the two variables at the same time instead of plotting it separately. But like I said, this is only good if your data is not so big and the features are not so many. Okay? So you can see the relationship, how well those species are separated in our data. You can visualize it. So, I mean, this gives you a single plot to visualize everything at the same time. What you have on the columns are just the histogram, just to, like, if you are looking at the relationship between the same variable, like sepal length. So just to tell you that, obviously, that's to tell you, this histogram, the diagonal, that's not what you should pay attention to, because it's the relationship between itself. So you should pay attention to the scatter plot, okay? All right, so let's move. Suppose you are now, as a data scientist, you've manipulated your data, you visualize it. Now you want to build your model. Now, this data here, they're already cleaned. So because this class is not for cleaning data, we've already looked at how to clean data last class. So all the data in scikit-learn, they are already cleaned, okay? So suppose you have that, you want to now start to build your model. So you can examine the type, like your data, the iris that I store, we can look at the type. Let me see. This is not what I want. Oh, sorry. So is the one, what I want is that of the data there. So it tells me the data there, the type is a numpy array. That data that I showed you at the very beginning, you know, they are stored as an array. That's a numpy array. So all the data in scikit-learn is actually stored as a numpy array. Okay, so now, remember I said at the beginning that while talking about machine learning, that your goal is to build a model that we predict well, that we generalize well, that we perform better on data it has never seen before. Now, you don't already have that data. All you have as a data scientist at the very beginning is your training data, is the data the organization gives you. So what you do, you need to split the data so that you use one part of the data to train it and the other part to test it. But in reality, split the data to 3 parts. 1, to train. 2nd, to validate it. After you have, you know, adjust all the parameters, blah, blah, and all of that, and your model is now good, you use the 3rd data to test it. But for this training, because the data that we're using are not so big, we're only going to be splitting it into 2. I will leave out the validation out for our main class. So and just focus on the training and the testing. So there is a function in scikit-learn that you can use to split your data. So you do from scikit-learn, you can put dots to see where the data, I think, is in the model selection module. Model selection, we can import our train, you can import. So split it, train test split, meaning split the data into training set, test set. So split is to split the data. Okay, so instantiate it. Okay, so we're going to split into our X train. You can use any variable, but you can use training set. I'm using this. Split it into S train, S test, Y train, Y test. Okay. These are just variable. You can use other ones, but this is the common one. So use this train test split function. Once you go inside, you want to split the iris, the data in the iris into the X train and X test, and then you split the targets into Y train and Y test. So this iris, this data here, that's what I want to split into the S train and S test. The target is what I want to split into this. Now, by default, my train test split the data in 75-25%, meaning it uses 75% to split, to train the data and use 25% to test. But you can overwrite it. You can use 30. Suppose I want to use 30%. or maybe I first show you here. Then there's an argument you need to set called the random state. It's just like a seed. You want to, if you want to get the same result every time, you need to set this random state because it's actually selecting your data randomly. So if you do not set this random state to anything, you don't necessarily have to use 0, just use a particular number. Okay, if you do not set it, every time you run this, it's going to give you a new training data and a new testing data, and it will give you a new model every time you're using that data. So once you use it, the norm is to set this so that you can always get the same result. Okay, so if I do this, I run this, okay, and then check the result, what I have done. Let's check the training, let's check the dimension of the training data. See, it split it from 150, it split it to this. We can check that of testing to see. See, it split that 150, so it's going to use 112 to build and use 38 to test. If I set the test size argument, suppose I want to use 30%, which is not advisable, at least for this small data. Test size 0.3, 0.3. So if I check it here again, you see, use 105.45. However, for small data, it's always good for your training data to be high and for your testing to be low. So, but let's maintain let's use the default, okay? Because the data is not large, okay? So I run that. Okay, so now we move to k-nearest neighbor. We want to build the model. K-nearest neighbor is an algorithm that is a supervised or classification algorithm that is stored in the k-neighbors classifier class. And it is stored in the neighbors module. How do you know that? You can say from scikit-learn, put dots and press tab. So if you scroll down, you have the neighbors, neighbors module. And then from there, if I pull from scikit-learn neighbors, import and press tab, it's going to tell me, give me the different stuff I have there. So you don't need to memorize this, just play around with it. So k-neighbors classifier, because I want to use k-neighbors. So first, you need to create an instance of that algorithm. Let's say I save it as KNN, k-neighbors classifier. Now, if by default, I mean, you can say I'm pressing Shift Tab now, it's not running. So sometimes I can run it and then come back there. So press Shift Tab now. See, to check the default, all the things you are seeing here, they are called hyperparameters, meaning these are parameters that they do not get trained. They do not get adjusted while you are building the model. They are already there. Okay, this parameter will not be adjusted. But to get a good and accurate model, some of these parameters, you have to adjust them. The most important parameter to adjust is this first one, n neighbors, meaning number of neighbors. By default, we have 5. That doesn't mean that's the best, but these were given to you by researchers who have experimented it and then see that, oh, I think 5 is a good number based on the accuracy they're getting. But you can test out all of that. So we're going to use the default for now, n neighbors to be 5. If you are not pleased, you have to set this argument to whatever number you want. So we create that, then we can fit the model. Fit means train your algorithm, train the model, okay? So just call this knn.fit, and then pass in your training data, strain, and then ytrain. Okay, so if you run that, it's going to give you just what it has actually, the parameters it used to train your model. Your number of neighbors is 5 and all of that. That's the major one you need to care about. Okay, there are 2, the metric and the neighbors. I'll talk on the metric later on. So if you want to now evaluate, you want to check the accuracy of your training data and your testing data to be sure whether the model overfit or underfit or generalized or whatever. So that's what this line is doing. Forget about from here to here. The main thing is this from KNN score. I just want to, decorate and make make my code look better. That's why I'm saying, okay, print, training accuracy, and then format is just to remove some unnecessary things, to format it. So the main thing, this call method is what gives you the accuracy. You are calling this call method on your KNN, this KNN, that this instance of the KNN bus classifier. What are you passing? I want to check if here I pass the X train and Y train, meaning give me the accuracy on my training set and then give me the accuracy on my testing set. I want to check them to be sure there is no overfitting. So if I run this, you can see the training accuracy is 97.3%. That's 0.973. And then the testing is this. So because the data is small, I mean, this is awesome. The testing accuracy here shows that there is no overfitting in my data. Why? The testing accuracy is a little bit higher than the training. Okay, so that means I achieved 97.4. But does that mean that's the best? That may not be. You have to test others. Okay, so here now I want to make predictions. So I create a numpy array, import numpy as np.array to create a new array. I just want to use that to test my data, to see its prediction, how well the model is performing. Okay, then you call on that KNN, this same KNN, you call on the predict method on it, then I pass my new data frame on it. So here I just want to check the prediction. Then here, this last line, I use this prediction to subset my target names. I want to see what is actually predicting. The class is predicting here. That's what I'm doing here. So I saw that if I give you this new measurement of sepal length, sepal width, petal length, and petal width, it's going to predict Setosa class. Okay, suppose we change this to, let's say 4.9, 1.8, and 4.2. It still predicts Setosa. So maybe we should, let's just check. I want you to predict some other class. So that's because of the measurement I'm supplying. Meaning it's looking at those measurements and testing it with the patterns he already saw in the data I used to train it. So let me see. I just want to see. You can see when I supply with this other measurement, it gives me another class that based on this measurement you supply, this is the species of this flower. Meaning if you supply another this kind of measurement and tell me to predict the class, I'm going to have Virginica. Okay, and then so you are done. But I just wanted to show this particular cell. I just want to say something on this. In the wild, in reality, your data will not always come. The measurement of each data will be different. Even here is different, but it's not that different. Let me show you what I mean. Let's put it here. This iris data. See. So the sepal length is from like 5.1, 4.9. There is another column, 0.2, 0.4, like that. You can see the range. They are different. So in reality, if you do not normalize your data, because most of these algorithms are actually calculating distance. That's the metric I said I was going to talk about. This metric, Minkowski. They are calculating the distance between those measurements. So if your data if the range is actually very different, it's going to affect the model you are going to build. So in reality, as a data scientist, you should normalize your data. Normalize means bring them to similar scale so that the distance will not affect my data. Why? How will it affect? A feature that has that the distance is very high, that has high range, we actually it will dominate your model. So you might think you are getting good accuracy, but that's not true. It's because that particular variable in your data has high range compared to all others. So if you supply it with new data with a different range, it's going to mess up. So what do? Scale it, normalize it. Fortunately, we have a function in scikit-learn that can help us do that. From scikit-learn pre-processing, because normalizing, you are trying to pre-process your data. Import standard scalar. What is standard scalar doing? For those in statistics who have some knowledge of statistics, this is giving you, is going to scale your data to have a mean of 0 and standard deviation of 1. So meaning scale the data to have mean 0 and standard deviation or variance of 1. So first instantiate it, create an instance of it, and I saved it in a variable called scalar. Then call on the fit transform to transform my string to, I still save it back as string. If on the testing, you only call transform, you don't call fit transform. You only fit it and transform it on the training, and then you only transform the testing. Okay, then here I say reinstantiate and refit. So suppose I just want to refit now, KNN, to be this my K nearest neighbor. Okay, suppose that's by the way. So I can even call fit on the same line, fit it with the new S trainer, the one that I have scaled. And then I can make my evaluation and all of that. What is it giving me? Found inconsistent number of samples. Yeah, I think he's using the other ones. What is wrong? Okay, so let's see. Let me comment out this and see what is going on in my data. So suppose let's create a new stuff here. So now that I have run this, let me see what I have, the X train shape. Okay, S test, shape. Okay, so if you want to see the transformation, if you call on this now, you can see they're already scaled to this format. Okay, so but let's see. So what is wrong? Fit it. KNN dot fit extreme. I have to remove these dots. And Y train. Okay, you can see. So here now, the training accuracy, it appears the training accuracy reduced, but the testing accuracy still remains the same. This might not be so obvious because your data is not that large, but and then the range is not that different. So it's better but it's a good practice. So check the range of your data. If they are different, scale it before you fit it, okay, so that it won't affect. You can say after we scale it, the training reduces. So, but suppose, this is where I'm going to stop. Maybe we'll move to logistic regression next class because I want you to practice. So let me quickly show this. I want to, because we've been using the default KNN, we've been using the default number of neighbors to be 5. As a data scientist, before you come out with a good model and present it to your organization, you have to have worked on it, check it with different, parameters. So I want to, my goal is to try, I want to try neighbors from 1 to 10, and then bring out the best, the one that gives me the highest accuracy. So I just did everything from the beginning, load my iris data, call on my train test splits, my k-nearest neighbor, and then I want to use the matplotlib. Okay, so the first line, this is my data, load iris. The next line, I split it, I've already shown you up there, split my data into the training and the testing. Now, what this other line is doing, I just want to set the neighbors I want to use. Range 1 to 11. If you remember the first line, range function is going to give you from 1 to, it's not going to include this last line. So it's 1 to 10. Okay, so I want to test neighbors from 1 to 10. I have an empty list that I want to put my training accuracy and my testing accuracy. That's what this line is doing. So this is the main thing, that I want to look through these numbers 1 to 10. So I said for This is just a variable name. For n neighbors, you can use any other one. You can use even ordinary n. For n neighbors in neighbor setting, meaning for n neighbors going from 1 to 10. So this first line is going to have one, just when n neighbor is just 1. It's going to test it. It's going to use n neighbor is equals to 1 year, fit it on the training, and then it's going to get the test, the training accuracy and testing accuracy. I use append to append it to this list. And it's going to go back and use when is n neighbor is 2, n neighbor is 3, up to when n neighbor is equals to 10. So when I'm done, I want to plot it to see. So here, I plot this range to be on the x-axis, then my y-axis should be training accuracy, testing accuracy. I put a label here. So because I put label here, that's why I'm using legend. Okay, if you don't have label here, you don't need to put legend. The X label, Y label, and show you. I can run this same stuff for you, and this is what I have. Okay, so this is where I'm going to stop before we do this exercise. So we're going to look at logistic regression next class. So that means you will not do this last solve. You're only going to do for KNN and then try out this question. But you're using a different data, the load breast cancer, in your data frame. So I'm going to stop sharing here and then split you into group. Okay.